Hello, hello. Coupling in proton NMR means that isolated sets of protons called spin systems give distinctive patterns. Understanding where proton coupling comes from isn't easy at first. Some profs will not even try to explain it. However, a superpower which makes NMR much easier is to be able to recognize patterns corresponding to spin systems in proton NMR. There are not that many spin systems, so recognizing one gives a huge clue about the structure of an unknown compound. I'm going to have a go at explaining the origins of proton-proton coupling before telling you what's really important to know. Watching my previous video on coupling in 13C NMR will help you a lot because that's easier to understand. The link for that is down under. Off I go. To illustrate why coupling occurs, think of two magnetically inequivalent protons on the same carbon. This can happen if that carbon is near a chiral center. HA and HB each experience a different field because the other proton has a magnetic nucleus, a nuclear spin. Pop. We just lowered the sample into the NMR against the counterflow of air, and it makes that nice plop sound as it seats in the magnet. Now the two protons are in the big magnetic field of the spectrometer, B0, and their nuclear spins align or oppose this. This can happen in two ways. HA and HB can both be aligned, or one can be aligned and one can be opposed. Therefore, perpendicular pulses applied to flip the nuclei between their populated levels are slightly different according to whether the other proton is aligned or opposed. That is coupling. Without any coupling, HA would just give one signal, a singlet. But with HB around, that signal splits into two, a doublet. The difference in chemical shifts between the two peaks in the doublet will differ on different spectrometers according to the size of B0. That's not helpful for comparing NMR spectra measured on different spectrometers. So instead of chemical shift, we express the coupling in terms of Hertz, equivalent to energy. And that's a constant called the coupling constant. Why is it constant? Because the local field experienced by one of those protons is not influenced by B0. It's influenced by the other. I want to remind you of the magic equation for coupling, 2Ni plus 1, where N is the number of nuclei doing the splitting, and I is their nuclear spin, which for protons and carbon is a half. Do you see how that applies to HA to give a doublet? If we sit on HB, we get exactly the same result, except it's HA doing the coupling. 2Ni plus 1 is in this case 2 times 1 times a half plus 1. That's 2, a doublet. What happens when magnetically inequivalent protons are on different but adjacent carbons? We see exactly the same coupling pattern because the field that HA experiences is still dependent on HB. The only difference is they're further apart and the coupling constant will be less. But what if there are two equivalent protons HB on the second carbon? 2Ni plus 1 is now 2 times 2 times a half plus 1 is 3, a triplet. And the distance between the peaks in the triplet will be JAB, the coupling constant. Why does the 2Ni plus 1 equation work every time? How do we explain that triplet? Well, for this coupling system, there's one chance that HBs will be both aligned. There's one chance that the HBs will be both opposed. And the situation with one aligned and one opposed is twice as probable. So we get a triplet and their intensities are 1 to 2 to 1. And the separation between the peaks is JHB, a different coupling constant for a different molecule. For the HB signal, there's only one proton doing the coupling, HA, just like before. So HB will occur as a doublet. The coupling constant for this will be exactly the same as JHB above, measured in Hertz. If there are no other protons in the same molecule close enough to perturb HA or HB, that's all the coupling we get. And it's called a spin system. The first two spin systems we looked at each had only one HA and one HB. The first one on the same carbon, the second one on adjacent carbons. The coupling pattern for that spin system is similar, but the JAB coupling constant varies. For spin systems like that, two doublets are always predicted. They can be perturbed, but let's say that for another day. However, for the third spin system we looked at, one HA and two HBs, the coupling pattern is different. A triplet and a doublet is always predicted. Here is a big conclusion, huge. Spin systems vary with the number of protons involved, but the pattern for each spin system is always the same. Coupling constants for different molecules vary, but the pattern expected for each spin system is basically the same. Okay, let's test this. Let's say there's only one HA and three HBs. That's a new type of spin system, so what pattern do we expect then? Three HBs are splitting HA, so then we expect 2 times 3 times a half equals 4. A quartet. Exciting. But all this is boring for HB. It's only being split by one HA again, so it appears as a doublet again. Let's do something to make HB more interested. Suppose there are 2 HAs and 3 HBs. That has to give us different spin pattern. Let's see if we can predict what it looks like. HA is still split into a quartet by the 3 HBs. That's the same, nothing has changed. But the 3 HBs are now split by 2 HAs into a triplet. Let's make a very handy generalization. Isolated ethyl groups, in other words, ethyl spin systems, always give a triplet quartet. Always is a huge word in science, not to be used lightly. Here it means that every time you eyeball a triplet quartet in a proton NMR spectrum, Sherlock's spectroscopy in your brain says, aha, Watson, an ethyl group. And there's another ethyl group clue. For HA, there's one chance that all the HBs will be aligned. There's one chance that all the HBs will be opposed. But there are 3 chances of 1 opposed and 2 aligned. And there are 3 chances of 2 opposed and 1 aligned. So we expect 1 to 3 to 3 to 1 for the intensities. Predicted intensities for the quartet then are 1 to 3 to 3 to 1. There's a trend here. Ideal splitting intensities follow Pascal's triangle. We usually see the quartet downfield of the triplet because CH2s tend to be downfield of CH3. Consider an oxygen attached to an ethyl group. Oxygen, being more electronegative than carbon, draws electrons to it, more for the CH2 than the CH3. So the CH2 is less shielded, more downfield, much more downfield. Do other spin systems have distinctive splitting patterns? Yes! For an isopropyl spin system, HA is split by 6 protons on the 2 methyl groups into a septet. And HB is a doublet again, split only by HA. Spin systems for 2 HAs and 2 HBs will always give a triplet pattern. Even if your brain is full and you don't quite understand coupling, make room for this. 2Ni plus 1 always simplifies to n plus 1 when I is a half. Intensities ideally follow Pascal's triangle. It's so useful to be able to look at a proton NMR and say, an ethyl group, or oh my goodness, a doublet septet, that's an isopropyl. That's the reason to learn this stuff. Sure, it can get more complicated because for larger molecules, there can be more than one spin system. But for introductory organic chemistry, one spin system is enough. Now sit back, relax, switch off your mind, and float downstream. Thank you very much to Eric and Marshall for giving me use of their studio in Southport, UK. And thank you too for watching this video all the way through to the end. Take care now. Bye-bye.